Okay, now uh, in 5 minutes, the water fall fold at a distance, suppose dx. Dx is given, dx equal to dx is given, dx equal to 0.012 0.012 0.01 meter, 0.01 meter dx is given. Water fault, the level of water decrease to dx, dx equal to 0.01 meter. Okay, now the mass of water evaporated in 5 minutes, mass of water evaporated in 5 minutes 5 minutes, we can write the mass of water, the mass equal to actually mass equal to volume into density, volume into density. And volume mass of water that evaporated at this volume, this amount of water evaporated, then the mass of this amount of water, mass equal to volume into density, volume, area A and length dx, then volume A into dx into density. Therefore dx is given 0.01 and density equal to 1 into 10 to the power 3. Okay, mass is find out, A into 10 kg, mass is find out, mass found. Now the heat required to evaporate this amount of water, equal to this mass, heat required equal to mass into latent heat of steam, evaporate, mass into latent heat, mass equal to A into 10 into latent heat is given into the question 540. Therefore 540 into 5 kilocalorie heat required. And this amount of heat is required to evaporate this amount of water. Now we know the equation Q equal to KAT theta 1 minus theta 2 divided by X. Q is the amount of heat energy, and here the heat energy, this is actually this Q. So we can write A into F equal to this one. Theta 1 or theta 2, okay, theta 1 is given, theta 1 suppose let this is theta 2 and this is theta 1. Theta 2 is given, theta 2 is given, theta 2 equal to 100 degrees Celsius, 100 degrees Celsius. Then K is given, K 0.12, 0.012 into A into time 300, theta 1 minus 100, and X is given 2 into 10 to the power minus 3. Now just from this just simplifying this equation, you can get theta 1 equal to 103 degree Celsius. This is the answer. Now we will discuss about the first law of thermodynamics. First law of thermodynamics. According to this law, a definite amount of heat energy is needed to do a definite amount of mechanical work. Suppose W is the mechanical work and Q is the heat energy. This work done, mechanical work done, is proportional to heat energy. Now W equal to JQ. J proportionality constant. This is also called mechanical equivalent. Moreover, the first law of thermodynamics can be explained in other ways. Suppose this law implies that the amount of heat supplied to a system must be balanced by the sum of the gain in internal energy of the system and the external work done. That is, suppose this is the amount of heat energy that is given to a system, and this amount of heat energy will be split into two sections. One is to increase internal energy of the system and work done of the system. This is also first law of thermodynamics. A reversible process and irreversible process. Reversible process means if a system and surroundings can be restored to the initial state from final state without producing any changes in the thermodynamics properties of the system is called reversible process. And reversible process practically take place at constant temperature, that is called isothermal process. Moreover, reversible process is possible if the changes in pressure and volume of the working substance must be take place at an extremely slow rate. Whereas the irreversible process is the process where the system with the surroundings can never be completely restored to its initial condition by reversing the controlling factors. And here all the changes in reversible process, all the changes occurred suddenly, like explosions, heat produced by friction, sudden unbalance of expansion. All the natural processes are the examples of irreversible process. The second law of thermodynamics. For Clausius statement, the second law of thermodynamics of Clausius statement is state that it is not possible to construct a device which operates in a cycle. While operating, it does not produce any effect other than transferring the heat from colder to hotter body. Just simplifying these sentences, in other words, we can say that it is not possible for heat to flow from colder body to a warmer body without any work having been done to accomplish this flow. Efficiency of a system. Efficiency means efficiency equal to output by input. Output by input. Output is work done and input is given heat energy. Given heat energy and the work done of the system. Output by input. If source of heat and engine and sink. Suppose source of heat, that is hot reservoir. Q1 is the amount of heat energy that absorbed by the engine for working, and Q2 is the heat energy that wasted and go to the sink, and the work done is W. Then efficiency equal to W by Q1, and where W means Q1 minus Q2. W work done means Q1 minus Q2. Q1 is the absorbed heat energy, and suppose this is 10 joule, and work done is equal to 8 joule, and then 2 joule is wasted. Therefore, work done equal to 10 minus 2, that means Q1 minus Q2 divided by Q1, and Q1 is the it given input, and this is output by input. We can also write this. Suppose at Q1, as the temperature of the source is T1, and this is sink is temperature is T2. Then we can also write T1 minus T2 divided by T1. Efficiency equal to this one. Therefore, efficiency equal to T1 by T1, 1 minus T2 by T1. There is a problem. This is problem number 2. A Carnot engine has an efficiency of 50% and whose low temperature reservoir is at 7 degrees Celsius. To increase the efficiency of it to 70%, how many degrees should the temperature of the high temperature reservoir be increased? That is, firstly, the efficiency of a Carnot engine. Carnot engine is given, this is 50% efficiency, eta equal to 50%. That is 0.5. Okay. And the low temperature reservoir, that is sink, the temperature of sink, that is T2, is given. T2 is 7 degrees Celsius. 7 degrees Celsius. 7 degrees Celsius plus 273 Kelvin. That is Kelvin. 280 Kelvin. We know eta equal to 1 minus T2 by T1, and eta equal to 0.5, 1 minus 280 by T1. Then T1 equal to 560 Kelvin. This is the first case where the efficiency is 50%. There the temperature T1. Temperature T1 means the source of temperature. Source of temperature or high temperature reservoir. High temperature reservoir means source of temperature T1 equal to 560 Kelvin. And for the second case where the efficiency increase to 70%. Therefore 70%. Therefore 70%. T2 with 280, it's okay. And T1 933.33 Kelvin. At the second case, we found T1 equal to 933. Therefore, the increase of temperature, the temperature of the high temperature reservoir should be raised by 933.33 minus 560 equal to 373.33 Kelvin. This is the answer. This is the answer of this question. Now 373.33 Kelvin of temperature should be increased to get the efficiency 70%. Now the Carnot cycle. Now we will discuss about the Carnot cycle. Carnot cycle. Source. This is a cylinder with a piston, cylinder and piston. This is source. This is a stand. This is sink. And there is the working substance. And the working substance may be air. Now there are 4 stages of a Carnot cycle. Where for the first stage, this cylinder with piston that is the bottom of this cylinder be placed in contact with the source. This is the first operation where the bottom of the cylinder be placed in contact with the source, and the gas or air is allowed to expand slowly. Suppose like this. At this stage, we call this is A point, where the temperature, the pressure P1, volume V1 and temperature T1. Here the piston go up for expanding. Because of expanding the gas, the piston will go up, and the temperature should be fall, but during the expansion, but this is compensated by absorption of heat from the source, but temperature will remain same by absorbing heat energy from the source. During the process, an amount of heat energy Q1 is absorbed from the source at constant temperature. Constant temperature. Okay, this is the first operation where this cylinder be placed with contact with the source, and this cylinder or gas will absorb heat energy from the source and the piston will go up. Work done and absorption of heat energy will be similar. For this reason, the temperature will remain same. Second operation, this cylinder is removed from the source and its bottom is placed in contact with the non-conducting stand. This is non-conducting stand. At the first operation, temperature will remain same. For this reason, this is called isothermal process. Isothermal process, that is, the gas expands isothermally. Now the second operation, this cylinder now plays to contact with the non-conducting stand. This is non-conducting stand. Here the gas completely isolated on heat enters or leaves the system during expansion. And here also the gas is allowed to expand, will expand, and the temperature of the system falls. Here the temperature will be false. Now this is here. And the piston will go up again and the temperature fall, but here there is no heat given or absorbed or absorption, no absorption. This is non-conducting stand. For this reason, this cylinder will not get energy or heat energy from this system, or this system will not given heat energy to the stand. Heat is not flowing in any direction. Now volume and pressure. Now volume increase, B, volume increase, pressure decrease, P2, V2, temperature decrease. This is actually A to B. This is the first operation. This is one. This is completely isolated from any other source, stand or sink. Then the point is A, and when it contact with the source, then we will get B, where pressure decrease and volume increase and temperature will remain same. Now this second operation will get point C, where pressure decrease, volume increase and temperature decrease. Temperature also decrease, T2. So this expansion is called isothermal expansion, and this expansion is called adiabatic expansion. Now, adiabatic expansion. This is P2C adiabatic expansion. Now, we third operation. The cylinder is removed from the non-conducting stand and its bottom is placed in contact with the sink where the temperature also T2. We got the temperature here. After falling the temperature, we got temperature T2, and the temperature of the sink also be T2. Now put this cylinder at a sink. Sink means this absorbed, mainly this absorbed heat energy from the from surrounding. Here the piston is actually pressed very slowly, and the gas is compressed. Here the heat generated and temperature should be increased, but the increased heat energy actually is given out to the sink. The heat generated actually for compressing heat will be generated, and this generating heat energy is actually given out to the sink, and temperature because temperature will remain T2, then the temperature will remain T2. The temperature was T2, and after compressing at the sink, compressing temperature should be rise, but it doesn't, because the excess energy producing here is given out to the sink. Therefore, the temperature will be same. So the compression occurred here takes place isothermally at the constant temperature T2. Constant temperature T2. Here the pressure rise, volume decrease, and temperature will remain same, T2. This is the third operation. Now the fourth operation. We just removed this cylinder and take place in contact with the insulating stand again. Here the compression will go on. The gas is compressed will go on, but heat taken or given heat energy this not happened at this stage. Therefore, the gas is compressed adiabatically until its temperature rises to T1. Its pressure and volume becomes P1 and V1, represented at the P1. Okay, here the compress is going on, then pressure will rise and volume is decreased and temperature will rise. Then we will get actually a point again, where the pressure, volume and temperature is P1, P1, T1. Therefore, uh, this is the fourth operation, adiabatic compression. Adiabatic means where heat is not absorbed, or heat is not given, heat is not flowing through to any other substances. Therefore, these are the four operation of the Carnot cycle.